The second laser ever invented was a cryogenic laser. It was also the first cryogenic laser invented. Back in the early days of lasers, they often tried to cool the laser material because it was difficult to make a laser at room temperature. Some of the reasons why you want to cool a laser is that it enhances some of the thermal properties of the laser, like thermal conductivity is increased, thermal expansion is decreased, thermal optic coefficients are more favorable. One of the major problems with lasers is what to do with the excess heat that's generated in them, especially for high power applications. So one way to get around that is to cool the laser. When you cool the laser, you change some of its thermal properties, and you can avoid problems that may occur like thermal lensing, in which you have an actual bulging effect at the end of the laser material, so it acts like a lens. And also avoiding problems with fracturing of the laser material, because as you heat it, it causes a stress in the material and the material can fracture. Part of what we want to do for lasers with remote sensing, efficiency is everything, because when you send a laser up in an airplane or a space, weight is a concern. So if you can make the laser as efficient as possible, that's a good thing. Cryogenic applications almost entirely across the range of what you would look at, neodymium, thulium, holmium, they increase the efficiency of the laser. You have lower thresholds, which is the energy required to make the laser operate. And you also have higher slope efficiencies, which is, it's sort of a ratio of the amount of energy you put in to the energy you get out. We want to look at the spectroscopic properties of the laser material. That includes the absorption cross-section, the emission cross-section, any energy transfer properties that may be occurring in the laser. The device in the background there, it's a cryogenic refrigerator. And it uses, there's a compressor that cycles liquid helium through the cryogenic chamber and cools the crystal in that way. So basically with that device, you put your laser material inside the chamber first, then you pump a vacuum on it, and then you can cool it down to very low temperatures. I think what I learned in doing my investigation is that there's not a lot of information in the literature on low temperature spectroscopic properties. In order to be able to make the laser, you need to know certain things. The wavelength of the transition that you're looking for, where you absorb and where the laser operates. You need to know what the emission cross-section is, the so-called laser gain parameter. And you also need to know how the lines broaden and narrow with temperature. I think the exciting prospect is that when we complete these spectroscopic measurements, perhaps there'll be the possibility for us to actually put it into application, make a laser or two based on cryogenic cooling, and see how efficient we can actually get them.